This is a hexaflexagon, an absolutely mind-exploding mathematical phenomenon. For those of you who are unfamiliar with this or just need a brush up, here's a quick recap. A hexaflexagon is a construction made from a loop of paper of folded equilateral triangles, like these ones here. To make one, you fold up from the front, fold up from the back, and then connect the two faces this way, and you're done. Now, the first thing one notices after making a hexaflexagon is a uniformity. The equilateral triangles fit perfectly into the center. This is by all means a regular hexagon. It has two faces, this one with a monster on a planet, and this frowny face over here. But what's incredible about this is that if you pinch each alternative edge like this into this interesting triangular shape, the center, which was previously compact, just decides to open up, revealing a third face with the star in the middle. If you're wondering where this face was before, let me go back. If we're over here and we have two faces, the third face must be hidden inside these flaps. And this is how this works. We use 9 equilateral triangles to make a hexaflexagon. If we look at both sides, that's 18 equilateral triangles. We have just two faces here, and each face takes 6 equilateral triangles for one hexagon. If we have 2, that takes only 12, which means inside the flaps there must be 6 more that are assembled to create a third face of 6 equilateral triangles as well. But what's more interesting than having a hidden face among two other faces is what happens to the same face after flexing. Take this one for example. Upon flexing, we reveal the third face with a star in the middle. But if we turn it over, we look at the same face but in a different state. It has changed its configuration in mathematical terms. Previously, all 3 planets were connected and the civilization was doomed to die. In this configuration, they're all separate and can live happily ever after. The same way, we look at this one with a star in the middle. Upon a single flex, it just disappears. And most importantly, we have this frowny face. After a single flex, it becomes a happy face. As I said, hexaflexagons have incredible powers. This particular flexagon is known as a trihexaflexagon, which means it has 3 possible faces that can be arrived at. But now let me show you something even more amazing. This. So at first glance, this seems like a normal hexaflexagon. We have presumably a face with a number 1 on this side and a face with a number 3 on this side. Let's start flexing. So upon the first flex, we go to number 2. Second flex, we go to number 3. We keep doing this, we make a pattern. 1, 2, 3, 1, 2, 3. Right? Seems pretty obvious. Quite similar to the ones that we saw before. But let's see what happens when we try to arrive at something from a different configuration. So let's flex it 1 and we reach here. Now let's see what happens when we flex this way. Boom, we arrive at a new face with number 5, and this makes 4 total faces. And that's not all. This is a very special hexaflexagon known as a hexahexaflexagon, which means there are now 6 possible faces that can be arrived at. As I said, there are 6 possible faces. Let's see if we can find them all. We'll start with face 1 in its first configuration. If we flex this way, we arrive at face 2. If we flex this way, we arrive at face 6. Let's try it in the second configuration. This is one in its second configuration. This way, we arrive at face number 5. And this way, we get to face number 3. Let's try face 2. So this is phase 2 in its first configuration. We go this way, we get to phase 5. And if we go this way, we get to phase 3. Interesting. Let's see where we can get with 3. This way we get to 4. And if I'm right, we've gone through all 6. There are an enormous number of possibilities to navigate your way through all 6 phases. But like any complicated mathematical phenomenon, there is a simple model. And this is what mathematicians came up with. In the center you can see the first loop that we found, the 1, 2, 3 loop. We have phase 1, 2 and 3 in their first configurations, navigating through themselves. Now if we take phase number 1, in its first configuration, we can go to phase number 6 by flexing along the other flaps. From phase number 6, we can go to phase number 3 But that's phase number 3 in its second configuration. And in fact, in its second configuration, it can only come back to phase number 1 unless you're flexing backwards. Otherwise, it's a closed loop. Phase number 3 in its first configuration, however, is a different story. It can go to phase number 4 or back to phase number 1. And in fact, it can also go to phase number 2 in its second configuration if you're flexing backwards. The same holds true for phase number 2. It can go to phase number 5 or phase number 1 in its second configuration. And these arrows are not one way. You can flex backwards all the time. If you remember earlier, we reached phase number 5 from phase number 1, but from phase number 1's second configuration. I hope that wasn't too complex to grasp. Now, you may wonder, a normal hexaflexagon is not very difficult to make. All you need are these 9 equilateral triangles and you fold them into a hexagon and it's done, right? And there you have it. Hexahexaflexagon, on the other hand, with 6 faces, would be slightly more complicated. And that's true, but it actually is made from the same basic principle. Here, let me show you. So, as I said before, if we have 3 faces in a trihexaflexagon, we need 18 equilateral triangles. And if we have 2 sides of the paper, that means 9 on each side. Same way, in a hexahexaflexagon, if we have 6 triangles, we need 36 equilateral triangles, which means 18 on each side. So instead of folding a loop of only 9 equilateral triangles, you fold one with 18. And with 18, you number them. You number it on one side 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, and leave one space here for gluing. And on the other side, you leave a space for gluing and label it 4, 4, 5, 5, 6, 6, 4, 4, 5, 5, 6, 6, 4, 4, 5, 5, 6, 6. You flip it over again, and now you loop around only on this face to make sure there are only 1s, 2s, and 3s, but make it 9 equilateral triangles. So we go like this, and we fold it into pattern that will make it 1, 1, 2, 2, 3, 3, 1, 1, 2, 2, 3, 3. And we end up with something like this. And this is our final result. And if you notice, these are 9 equilateral triangles. The same way we did it with the trihexaflexagon, we do it with this one. We fold up from the front, fold up from the back, and we glue these 2 sides together. And that's it. It's done. And that's how you end up with a hexahexaflexagon like this one. Some of you may wonder as to what is the purpose of mathematical phenomena such as the hexaflexagon. And to be honest, I think it's just fun. Despite the increasing amount of importance given to pure mathematics in the 19th century, math has always been more of an applied subject. And with applied mathematics comes recreational mathematics, where mathematicians tinker and innovate with concepts that they find appealing. And this encourages progressive thinking. In fact, one of the most notable endorsers of the hexaflexagon was Professor Richard Feynman, who at a point was ready to believe that the hexaflexagon, moving through an hexaflexagon, could actually model the way that light navigates the space-time fabric. Though with advances in nuclear physics that has since been disproved, but that's not the point I'm trying to make here. With recreational mathematics and concepts such as the hexaflexagon, mathematicians and students like us are encouraged to explore math with freedom and creativity. And that's what I find the best part about the hexaflexagon. Thank you. I hope you enjoyed.